Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. This lecture is part of the lecture series on power system operation and control course. And in this lecture, I will explain the automatic generation control, which is abbreviated as AGC. So, the automatic generation control actually defines the variation of frequency with respect to the change in load or change in power generation of a generator. So in AGC, we have a interconnected network of a power system, and in that interconnected system, you can observe two areas. This is area one, and this area has its own generation, its own load, and its own losses. Similarly, this is area two, and this area also has its own generation, demand, and losses. And these two areas can be interconnected with each other such that if we have a deficiency of power in second area and if we have a surplus power in area one, then the reliability of the power system can be enhanced by injecting the surplus power from the first area to the second area. So this is how interconnected system works. And if we have more generation but less load demand, the frequency of the power in that area will be high. And similarly, if the load or consumption in one area has increased, then the frequency will reduce, right? So this is the net interchange power between two adjacent areas, which is um, abbreviated as P int. So P int is the interchange power between areas, and this is equal to PG1 minus PD1 minus PL1. So PG1 is the generation in this area minus the demand minus the losses will be equal to the net interchange power at this tie line interconnection. Similarly, if we have a surplus power generation in area 2, then that surplus power will move towards the area 1, and in that case, P interchange will be equal to Pg2 minus Pd2 minus PL2. Tie line allow the sharing of generation resources in emergencies and economies of power production. It also shares the responsibility to maintain frequency. Frequency changes when the load changes, and when we have a frequency deviation with respect to the load, then we will have two aspects, right? So first aspect is area control error, right? It is abbreviated as ACE, and then we have energy control center. So area control error gives measure of deviation between desired and actual system frequency combined with the deviation from the scheduled net interchange. So this is area control error, and to remove area control error, energy control center sends command signals to the generating units to control outputs to restore the net interchange power to scheduled values and restore the system frequency. This is done by computer-based automatic generation control. So whenever we have an imbalance of power consumption and power generation, the frequency of the system will disturb. In that case, we have to maintain the balance between the power generation and power consumption. So that balance can be achieved by either injecting the surplus power to the adjacent area or by extracting the deficient power from the adjacent area to maintain the balance. So if we have successfully maintained the balance of energy generation and consumption, then the frequency of the system will be restored. So boiler turbine generator, we can have the example of boiler turbine generator. And in these types of generators, there are turbine speed governors, and they actually monitor speed and control the throttle valve to adjust the speed. So whenever we have more load but less generation, the speed of all the generators will reduce, and due to that reduction in speed, the frequency of the output energy will also reduce, and we have to increase the generation in that case. So that generation can be increased by opening the throttle valve more, right? So that more fuel or more steam can be injected into the generator. And when the steam inlet or the fuel inlet to the generator increases, the speed actually restores, and the system or the generator will also increase its output power. Okay, so when its speed increases and its speed will be restored and power generation will also be increased, the frequency will also be restored. So that type of control is called supplementary control. So in automatic generation control, the most important characteristic is the droop characteristic. And a droop characteristic is actually a curve between the output power of the generator and the frequency of the output power. So here you can see that at no load, the frequency of the generation is F2, and this is the rated power, which is PGR. And at rated power, the frequency is equal to F1, such that F1 is smaller than F2, and we have a decreasing droop characteristic curve, right? And the slope of this curve is negative since this is a decaying frequency curve, and the slope is equal to minus R, right? So whenever we increase the load, the frequency of the output will decrease. And in that case, we have to apply the supplementary control by controlling the throttle valve of the generator. And that supplementary control will shift this droop curve upward such that the new system frequency becomes equal to the actual or desired system frequency. So this can be observed in this figure. Here you can see this is our initial power generation, and at this point the frequency is this, right? So when we increase our load, the output generation will also increase and the frequency will reduce to this point. And at this point, we will apply the supplementary control, and that supplementary control will shift this whole droop curve upwards, and the new droop curve will lie over here. And you can see at this point, the new system frequency is this, and this is exactly equal to the old system frequency. So this is our initial frequency, this is our new frequency, and after supplementary control, this is our final frequency. This is delta F deviation in the generation frequency. This is delta PG deviation in the output power of the generator. This is PG naught, and PG is equal to PG naught plus delta PG. This point is PG, and it is equal to PG naught plus delta PG, and RA is equal to per unit deviation in the frequency divided by per unit deviation in the generation, right? So whenever we are converting our actual quantities to per units, we have to divide them by the rated values. So F2 minus F1 divided by the rated frequency is the per unit difference or per unit deviation in the frequency. Similarly, PGR minus 0 divided by SR. So this will give us the per unit deviation in the output power, and SR is the megawatt base. So this is the base value, and PGR is the rated value of the generator. F2 is the frequency at no load. Okay, so this is our F2, this is our F1, and F1 is the frequency at full load. FR is the rated frequency, and SR is the megawatt base. So this is our RA, which is the slope of this droop curve. Now we can evaluate the slope of this curve in actual units, right? So the slope of this curve in actual units will be equal to F2 minus F1 divided by PGR, right? F2 minus F1 divided by PGR, and that will be equal to capital R, okay? So F2 minus F1 divided by PGR is equal to capital R, and from this equation, we can say that this capital R is equal to RA multiplied by FR divided by SR. So after rearranging this equation and substituting F2 minus F1 divided by PGR equal to capital R, we can get this equation. So R is equal to RA multiplied by FR over SR. and R is equal to F2 minus F1 divided by PGR, and F is equal to F naught minus delta F, and delta F is equal to minus R delta PG. So this minus R delta PG actually comes from this equation, right? So you can see this is our delta F, and delta F is equal to F1 minus F2, right? F1 is our new frequency, F2 is our old frequency. Old frequency at no load is F2, new frequency at rated load is equal to F1. So delta F is equal to F1 minus F2, and F1 minus F2 will be negative since F1 is smaller than F2. So we have a negative sign over here, and delta F will be equal to F1 minus F2. And from this equation, F1 minus F2 is equal to minus R multiplied by PGR. And PGR is actually equal to delta PG, right? Because delta PG is equal to PGR minus 0. So delta PG is equal to PGR. So delta F is equal to minus R times delta PG, right? So that can be written as minus R is equal to RAFR over SR multiplied by delta PG. So we are moving towards very important set of equations which we will use in solving our group problems. So from here we can write delta PG equal to minus SR over FR into delta F over R1, right? So delta PG, so after rearranging this equation, we can write delta PG equal to delta F over FR into SR over RA, right? So for the first generator, delta PG1 will be equal to minus SR1 divided by R1A into delta F over FR. Similarly, for the unit 2, it will be delta Pg2 equal to minus SR2 divided by R2A multiplied by delta F over FR. And for unit I, this will be the expression. And for a general unit K, delta PGK equal to minus SRK divided by RKU into delta F over FR. So overall delta P will be equal to the sum of all these delta PGs, right? So delta P will be equal to this plus this plus this. So minus can be taken as common, and delta F over FR can also be taken as common. And then we will have SR1 over R1A plus SRI over RIA plus so on up to SRK over RKU. And delta F over FR in this case will be equal to minus delta P divided by this whole expression. So this is our delta F over FR. Now we can evaluate the individual PGs. So delta PGI is equal to minus SR1 over R1A multiplied by delta F over FR, and this is our delta F over FR. So this minus sign will be cancelled out with this minus sign, and delta PGI will be equal to SRI divided by RIU divided by this expression multiplied by delta P. So this is our delta PG for the individual generating unit. Through such coordinated control of set points, it is possible to bring all the units of the system back to the desired frequency of node. So this causes the area to absorb its own load changes. It provides the pre-arranged net interchange with neighbors, and it ensures the desired economic dispatch output of each area plant, and it also allows the area to do its share to maintain the frequency. So maintaining the system frequency is extremely important because load changes throughout the day, as we all know. And if the load is not stable, the frequency will also be not stable. So that instability in the frequency of the generators can harm our end equipment. So let's solve a very simple example on this Droop characteristic curve. And in this example, we are given two units. The rated frequency of the system should be 60 Hertz, and the total load is given as 700 megawatts, and that 700 megawatt is divided between these two units. The rated output of the first unit is 600 megawatt, which is our SR1. The rated output of the second unit is 500 megawatts, which is SR2. Similarly, speed droop is given as 4% and 5% for the two units. And the first unit supplies 400 megawatts, and the second unit supplies 300 megawatts, since our total load is 700 megawatts. Now let's assume that our total load increases to 800 megawatts. Initially it was 700 megawatts, now it becomes 800 megawatts. So our delta P is equal to 100, right? So delta P is equal to Pg2 minus Pg1, and that will be equal to 100, and delta F over Fr is equal to minus delta P over this expression. So this is the same expression that we have derived in this slide, and you have all the quantities, and you can evaluate this value of 0.004 per unit, right? So this is our per unit deviation in the frequency. Actual deviation in the frequency will be evaluated by multiplying this value with the rated frequency, and you have to note that this is minus negative value. So this minus sign has been missed by me, but we have a negative sign over here, and delta F will be equal to this value multiplied by 60 hertz. So that will be equal to minus 0.24 hertz. So our new frequency will be equal to 60 minus this. 60 is the no load frequency, and the new frequency F2 will be equal to 60 minus this. So that will be equal to 59.76 hertz. So this is the deviation in the frequency as a result of 100 megawatts of load increment. Now delta Pg1 can be evaluated from this expression, right? So since we have two units, so we have two terms at the denominator only, and just put all the values over here, and we have 60 megawatts as delta Pg1. Similarly, delta Pg2 is calculated to be 40 megawatts. So that difference of 100 megawatt has been assigned such that 60 megawatts of that difference will be handled by the first generator, and 40 megawatts of that excess generation will be contributed by the second generator. Now we will discuss the supplementary control, and we are given that only one unit will adjust the output to restore the frequency, and that unit is actually the first unit, right? So unit 1 will actually adjust the output to restore the frequency, and this is the droop curve of the first generator, this is the droop curve of the second generator. This is our initial frequency, which is 60 hertz, and you can see that this generator was operating at 60 hertz, and this generator was also operating at 60 hertz initially. Now, as the load increased from 700 megawatts to 800 megawatts, these points will shift downwards, right? Because initially this was the system frequency, and this was the power share. PG1 was equal to 400 megawatts, PG2 was equal to 300 megawatts. Now, since delta PG1 is equal to 60 megawatts, so that generator, the first generator, will shift its output power from 400 to 460 megawatts, and the frequency will also reduce to 59.76, which we have just calculated. And the second generator will generate a power of 340 megawatts, because the delta Pg2 is equal to 40 megawatts. So still no supplementary control has been applied. So the supplementary control has to be applied by the first unit only. So this first unit will increase its power further, such that all the load increment is contributed by the first unit. So that first generator will increase its power from 460 megawatts to 500 megawatts. So its operating point will move from this point up to this point. So its droop curve will also shift upwards, such that the system frequency is restored at 60 hertz, and whole 100 megawatt uh, excess power has been contributed by the first generator. So its output power will be from 400 megawatt to 500 megawatts. The droop curve will also shift, And for the second unit, initially it went from 300 megawatt to 340 megawatts, but since the supplementary control has been contributed by the first unit only, so it will move backward to its original operating point. So it will move from point B to point A again. So for the second unit, this is our point A and this is also our last point C. So points A and C are similar and this is our point B. But for the first unit, this is our A point, this is our point B, and this is our point C. So this is how we can apply supplementary control to restore the frequency and to assign the load sharing between the generators. So that supplementary control can also be applied to the second unit. So in that case, point A will be over here, that will be point B, and point C would be the same point as point A. And that the second generator will actually contribute the whole 100 megawatt excess power. So it will first move from 300 to 340 megawatt. Then it will move from 340 megawatts to 400 megawatts. And its new operating point C will lie somewhere over here. Okay. And that point would have uh, corresponded to 400 megawatts and the frequency would be 60 megawatts. Similarly, we can use both the units to uh, contribute the supplementary control, right? So this is the third case. So in that case, this is our point B, this would be our point B, and point C would be the same point, but over here, right? So that droop curve would have shifted upwards, but that droop curve must have passed from this point, right? So the final generation of the first unit would be 460 megawatts, and final generation of the second unit would be 340 megawatt. So that would be the final movement or final adjustment of the operating points in that case, if both the units are applying the supplementary control. So this would be our point A, this would be our point B, and this would be our point C. Similarly, this would be our point A, this would be our point B, and this would be our point C. So I think you have understood the concept and the shifting of these operating points as a result of supplementary control to restore the frequency of the system. And I hope you have enjoyed and understood the mathematical model of the automatic generation control and the shifting of the droop curve as well. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.